Hello everyone. Before starting the lesson, try this warm-up. Graph the following relations. So I have three different equations in three different forms. See if you can remember how to turn these into a graph. So pause the video and try this on your own. Remember, if you know where the vertex is, and you know the direction of opening, and you know the step pattern, you can find the other points and draw a curve through all of your points. And if you know the x-intercepts, you can find the axis of symmetry, it's halfway between those two values, and use that in the equation to solve for what y would be. Now you have the coordinates of the vertex. And if you know the step pattern, you can find all the other points. And if you have the standard form, make it into a more useful form, like the vertex form, and then you can know what the direction of opening, step pattern, and the vertex are, and you can figure out all your points. If you have difficulty with the graphing, you should pause the video and get some help with this warm-up before you move on to the lesson. In this lesson, we are going to take what we know about quadratic functions and apply it to solve problems. So we're going to use quadratic functions to solve problems, and it's going to require you to use all of the skills you've learned so far in the unit, all the algebra and all the graphing skills. Now, when solving problems, sometimes you need to be able to develop an equation. That's what I'm going to focus on in the first little bit. Because once you have an equation, it can actually help you solve problems a little better. So let's start with this example. Here I have a graph, and my goal is to make an equation of this function. So I'm going to go through three steps. I'm going to list what information do I know, what form is most useful based on that information, and then what is the equation. So when I say what information do you know, what I'm thinking of is those major points, the vertex, the x-intercepts, or the y-intercept. Do you know any of those? Well, in this case, the only major point we know is the vertex. It has coordinates -5, 2. So if we know what the vertex is, what form of the equation is most useful? The standard form, the factored form, or the vertex form? Well, standard form, you get the y-intercept from that. Factored form, you can see the x-intercepts, but I don't know any of those. So vertex form, you can see what the vertex is. So the vertex form is going to be the most useful for actually making an equation. Remember, D and C are the coordinates of my vertex. I already know what those are. I need to figure out what the A value is, and then once I know what that is, I have my equation. So A, remember, it tells you the direction of opening and the step pattern. So let's reverse that. Let's work backwards. What is the direction of opening? Well, it's opening up, so I know A is positive. Now, what's the step pattern? We'll go over 1. How much do I go back up to get to the function? A half. Let's see if half steps are what it is. The basic step pattern is 1, 3, 5. So if it's half as much, it would be half. 1.5, 2.5. It looks like that's what my step pattern is. So if you know your step pattern, look at that first step. That is actually what your A value is. So now that I know the vertex and the direction of opening in this first step, I know what my A value is and my D and C values. I plug them into the vertex form, and there's my equation. So this equation models this graph. So now you try for this function. Here I have the graph. Think about what information do you know, what form is most useful, and then make the equation. So pause the video and try this on your own. For this one, you might have got one of these two answers. If you looked at the vertex, you could make the vertex form equation, but if you looked at the x-intercepts, you can make the factored form equation. Notice that the A value is the same in both. We got that by noticing we're opening down, so it's negative. And the first step is 2. So A is -2 in each case. Remember, with your x-intercepts, if your x-intercepts are -1 and +3, it's x plus 1 and x minus 3 in the factored form. Same with your x-coordinate of your vertex, it's +1, so it says x minus 1 in the vertex form. So both of these answers are correct equations for this function as shown. All right, now here I don't have a graph, so I'm going to determine an equation for the quadratic function that has a vertex 0, 4 and passes through the point 3, minus 5. So if I draw a sketch, this is what it would look like. The vertex is 0, 4. It goes through another point at 3, minus 5. That's down here. So based on that, I know that my function has to be opening down, or else it wouldn't be able to go through this point. But I don't really have enough information right here to figure out what the step pattern is, because I don't know what the point is when x is 1. So I can't really solve this the same way as I did when I had the graphs given to me. But I do know the vertex, so I'm going to start with the vertex form of the equation. I'm going to plug in what I know. I know the coordinates of the vertex, so I know d is 0 and c is 4. Now x minus 0 is just x, so I'm going to simplify this. X minus 0 squared is just x squared. I still don't know what a is though, so I'm going to have to figure that out. And that's where this other point comes in. I know at this point on the graph, x is 3 and y is minus 5. So I'm going to plug those values in for x and y. So x is 3, y is minus 5. Here's my equation. Now 3 squared, I can do that. It's just 9. So now I have an equation. A, whatever that is, multiplied by 9, and then add 4, I get an answer of -5. So I'm going to start to solve this equation for A by doing opposite operations. So I'm going to subtract 4, then I'm going to divide by 9. And when I do that, I end up with a value of -1 for A. So now that I know what A is, I can go back up here and write out what my full equation is. So if A is -1, it's -1 times x squared, or just -x squared, and then plus 4. This is the equation of the graph. So whatever major point you know, that determines what form of the equation you should start with. If I knew what the x-intercepts were, I would start with the factored form. But here I knew what the vertex was, so I started with the vertex form. Then I plugged in all the information I did know, and then I took another point on the curve and substituted in the x and y values and solved for my a. Once I knew what a was, then I knew what the full equation was. And that process will work if you know one of the major points and another point on the curve, then you can find the equation. So why don't you try this one on your own? Determine an equation for the quadratic function that has vertex -2, -3, and y-intercept of -1. So you know the vertex and another point, just like we did in the previous example. So pause the video and try this one on your own. Well, here you are, vertex form. So we know that d is -2, so x minus -2, that's x plus 2. C is -3, so plus -3 is just -3. I know another point, x is 0, y is -1 at the y-intercept. So x is 0, y is -1, and now I proceed to solve. 2 divided by 4 is 1/2. If you put 0.5, that's acceptable. This is the equation of the quadratic function. Now, when solving other problems, you may need to determine key points on the graph. If you need to determine where the x-intercepts are, use the factored form. If you need to determine where the vertex is, use the vertex form. Or, I showed you earlier in a previous lesson how to find the vertex a different way. You find the axis of symmetry from the x-intercepts, and then you can use that to find the y-coordinate of your vertex. If you need the y-intercept, you can use standard form or just substitute x equals 0 into the equation. You may also need to solve an equation, and in the previous lesson we talked about solving by factoring or solving using the quadratic formula. So all of these ideas come into play when we're dealing with different applications of quadratic functions. Now I want to walk you through a word problem because those are typically the types of questions that students have the most trouble with. Boris wants to drive his car off a ramp. So I've got a nice little picture here for you to picture what's going on. He's going to drive up the ramp and he's going to launch. And what's going to happen? Well, the car's going to go up, but it's probably going to come down at some point. So we have this function to model that. The path of the car can be modeled by the function shown below, this one, where h is the car's height above the ground, vertical height, and d is the car's horizontal distance from the edge of the ramp. So at the edge of the ramp, the car's distance is 0. The distance increases going to the right. Both of those measurements are in meters. So how high is the edge of the ramp? Think about what this would look like on a graph. If it helps, draw a picture. We're measuring distance from the edge of the graph, so that tells me where I'm going to put my y-axis. Distance increases to the right. He's going to drive up the ramp and it's going to come back down. So I can see the beginnings of a graph here. Now how high is the edge of the ramp? Well, that's the height here. So think about what point that is on the graph. That's the y-intercept. Now I know the y-intercept, I get that from the constant in the standard form, and that's what I'm given, standard form. So I can tell the coordinates of the y-intercept. That tells me the edge of the ramp is 4.8 meters high. So think about how this would look on a graph and what point do you need to know, and does the equation given to you show you what that value is. Part B, how high will the car be when it is 2 meters away from the edge of the ramp? So when you get a question like this, think about what are you asked to find and what value do you know? You've got two variables, height and distance. You're asked for the height, so you don't know what h is, and you're told it's 2 meters away, that's distance. So if you want height, you need to plug in a value for distance and calculate the height. So I'm going to use my equation, and in function notation, I'm finding the height at 2 meters distance, h of 2. So d is 2, replace d with 2, and do the calculation. I get 6 meters. So if you are told a value for one of your variables and you're asked to calculate the other variable, just substitute the number you know into the equation and solve for the other variable. Now I'm just switching the screen here, but this is the same function equation that we're talking about in the last slide. When the car is 5 meters above the ground, how far away from the ramp will it be? Okay, when the car is 5 meters above the ground, that 5 meters, that's the height. How far away from the ramp will it be? That's the distance. So this time we know the height, we're solving for the distance. So I'm going to plug in, the height is 5, and I don't know the distance, so I don't change anything over here. But here I have an equation, I'm asked to solve for d. This looks like I'm solving a quadratic equation, so I need to make sure my equation is equal to 0. So I'll subtract 5 from either side and I end up with this equation. I could try solving by factoring, but I don't like the looks of that 0.2. I'm not even going to attempt that. I'm just going to use the quadratic formula. I'm not going to get into the details of the quadratic formula. If you need a refresher, you can go back to the previous lesson where I talked about that. But when you plug in your values for a, b, and c in the quadratic formula, and you do the calculation, you'll get 2 possible answers for the distance here. And now, at this point, because we're talking about a practical example, we need to see if these answers make sense practically. The distances are both positive, which means they're both in front of the ramp, which makes sense. So both of these are valid answers. So I can say the car is 5 meters above the ground when it is 0.2 meters away from the ramp, and again when it is 4.8 meters away from the ramp. Now, you might be wondering, why do both of these answers make sense? Remember, the car's going up and down again, so it's going to reach the same height at two different points, on the way up and on the way down. Okay, part D. Boris wants to launch his car across a canyon that is 7 meters wide. Can he make it across the canyon? Again, if we think about what this would look like on the graph of height versus distance away from the ramp, he's going to start at the edge of the ramp, he's going to go up a little bit and then back down. We want to see if he can get across the 7 meter wide canyon. So we need to know how far away he's going to land. So we want to know the distance at what height? When the height is 0, when he's on the ground. So I know height is 0, so replace height with 0, and now I'm going to calculate what d is. Well, that looks a lot like the last question, so I'm going to solve it in a similar way. So when I use the quadratic formula to solve this equation, I get two answers, -3 and 8. If I think about where that would be on a graph, well, -3 is over here, 8's over here. These are the x-intercepts I just found. So now I can answer the question, can he make it across the canyon? The canyon's 7 meters wide. Well, if his ramp's right at the edge of the canyon, he'll land 8 meters away. That'll make it over the 7 meter canyon. So I can say he will be able to cross the canyon. Now, same situation. Boris now wants to launch his car over a wall that is 7 meters tall. Can he make it over the wall? Now, graphically, this is what I know. I know the x-intercepts are -3 and 8. Can he make it over the wall? Well, I need to find his maximum height to see if it's even possible for him to get over a wall that's 7 meters. So if his maximum height is over 7 meters, then yes, I can say he could make it over the wall. But if his maximum height is not above 7 meters, he's not going to make it over the wall. So really, you're finding the vertex. There's a few different ways you could do this. I'm going to show you the simplest, most straightforward way of finding the vertex. But you could just you could turn this into the vertex form by completing the square. That's a lot of algebra work to do. The other way, the simpler way that I was mentioning, was first find the axis of symmetry. If you know the x-intercepts, that's easy to find the axis of symmetry. It's halfway between -3 and +8. Well, you can think about it on a number line. You can count back and count forward till you find the middle, or you can take the average of the two x-intercepts. Either way you do it, you get 2.5 as the middle between -3 and +8. So the axis of symmetry is d equals 2.5. Now, if we want to find the height at that point, we just have to substitute 2.5 in for d. Wherever we see a d, it's now 2.5, and do the calculation. So the height at 2.5 meters away is 6.05 meters, which means he's not going to make it over the wall. Because the wall's 7 meters high, he's only going to get a maximum height of 6.05 meters. Poor Bob. So now you've seen the kind of thinking you should be doing when you face a word problem dealing with quadratic functions. I'd like you to pause the video and try this example on your own. I'm not going to read through it right now. You can do that. Just pause the video and try this. Here's my answers. We know the launch height, that's the y-intercept. We know the maximum height and when it happened. At a distance of 10 meters, it was 40 meters high. So we can make a sketch of the graph. Write an equation to model the flight path of the firework. Well, we're going to use y and x to represent the height and distance. I know the vertex, so I'm going to start with the vertex form equation, plug in my d and c values. Now, substitute in the other point that I know, x is 0, y is 2, to find out what the a value is. A is -0.38, so the equation is y equals -0.38 times x minus 10 squared plus 40. in vertex form. After the firework reaches its maximum height, it continues to travel an additional 1 meter horizontally before it explodes. Now, if you're adding 1 meter to the distance at which it reaches its maximum height, well, that was 10 meters. You're going 1 more meter. That's a value of 11. So when x is 11, put that in the equation, find the height. It was 39.62 meters high when it exploded. And lastly, at what other horizontal distance is the firework at the same height as in part C? So at the same height as when it exploded. Think about symmetry. If it exploded 1 meter to the right on the graph, well, symmetry would say the same height would happen 1 meter to the left of the vertex on the graph. So that's 9 meters. You can use symmetry to answer this question. No matter the word problem, you're looking for similar things. Either the vertex or the x-intercepts, you might have to plug in a value for y and solve for x, or plug in a value for x and solve for y. And to do that, you're just going to use the algebra that we've been talking about in this unit. It really just comes down to practice, so that's what I have for you. There's 2 page references. On page 250, just question numbers 3 and 4. Page 239, there's a lot of questions on there. I'm saying choose at least 5 of those questions to get enough practice, but you might need more than that. It really depends. So practice, practice, practice. When you run into difficulties, reach out for help, and I'll do my best to assist you.